All right, hello everyone. Hope your Friday is going well. Today we're doing proof writing day 1. This is learning target 6. I can prove statements using formal proof arguments with parallel line properties. This is our last learning target of the unit. Today we're just going to get some more information, make sure we understand how to make conclusions with certain things like linear pair postulate, vertical angles, so that on Tuesday we can start writing actual proofs. If I go too fast at any point, you can pause the video, rewind it, pause it, and write down whatever you missed. So there are two worlds. We've talked about this the last week. There is the algebra world and the geometry world, and we've been talking about how do we know we're in which world. Okay, what symbols? So the symbols are going to tell us which world we're in. So an equal sign is going to be the algebra world. If I'm given anything with an equal sign, that means I'm in the algebra world, and I either need to switch to geometry or I'm doing an algebra proof like we did this Monday. If I have an equal sign and I'm in the algebra world, I have to use the little n. If I'm naming an angle, I have to say the measure of angle ABC because I'm talking about an actual quantity, a number, when I use equal signs. And when I do segments, I have to drop the segment symbol on top. So for instance, I would have CD equals BC, no line on top. The geometry world uses symbols like congruent or perpendicular. All those symbols that we've been learning in this class are going to indicate that we're in the geometry world. But more importantly, we're going to probably use the congruent symbol a lot. We'll need to use just the angle of ABC. You would drop the M when we're using the congruent symbol. And with segments, now we need the line on top to indicate that it's a segment. So that's the difference between algebra world and geometry world. And if I'm given an equal sign, I know I'm in the algebra world. If I'm given a congruent symbol or any other geometry symbol, that means I'm starting off in the geometry world. So more properties for both worlds. We have the reflexive property. When we talk about reflexive property, I want you to think that everything is equal to itself. So for algebra, we are going to use the reason. So if I'm using reflexive property in a proof, this would be my reason. And we would say reflexive property of equal. For geometry world, if we needed to use this property, this would be our reason. And it's going to be a reflexive property of congruency. here to give you 3 different examples of when I'm using this property, what it looks like if I'm using numbers with this property or if I'm using segments or angles. So in the algebra world, if we have numbers with this property, we're saying A is equal to A. Okay, think of it as 5 has to be equal to 5. Okay, everything is equal to itself. And the best way that I remember that is if I look into a mirror, I'm looking back at myself, and it's going to be an equal image because it's me. So it's a reflection of me, reflexive property. That's just my silly way of remembering it. We won't have a numbers version for the geometry part. Segments, if I want to use reflexive property using algebra, I could say that AB is equal to AB because everything is equal to itself. But as soon as I write it for geometry, I have to put that segment symbol on top. Okay, because now I'm using congruent instead of equals. So everything is equal to itself. With angles, I'm going to use the little m for the algebra world because I have an equal sign in the algebra world. But as soon as I write it for the geometry world, that m goes away and I'm putting a congruent symbol in. So again, those tiny details are going to be a big deal because if I write my statement wrong, that makes my whole proof invalid because I'm working off of an invalid statement. And I've been taking off a lot of points for those little mistakes over the years, so please slow down, look at the details, make sure you have it written correctly. The next property we're going to learn is symmetric property. When we do symmetric property, just think you're switching the order. And when you switch the order, it still means the same thing. Okay, so for instance, if I have x equals 2, 2 equals x is also the same thing. So we can say order doesn't matter. Okay, sometimes we need to do this because we have to match our prove statement. And our prove statement will be in one direction, and our work might be in the other. So we'll have to take a step and flip it and say it's because of the symmetric property. So for the algebra world, okay, if I were to give this a reason in my proof, I would be writing this as my reason. Symmetric property of equality because it is the algebra world. And for geometry, we're using the symmetric property of congruency. That would be our reason if we're in the geometry world and using this property. So again, I have the same chart. I'm going to show you examples if I had numbers or segments and angles. So in the algebra world, if I had numbers, what essentially this is saying is if A is equal to B is true, then B equal to A has to also be true. So it doesn't matter how I write it, it's still the same thing. It's still saying that A and B are the same number. The order doesn't matter. For segments, because remember there's no numbers for the geometry, so we're going to skip that box. So if I'm doing segments, if AB is equal to CD, then CD is equal to AB. I'm just flipping it around and it means the same thing. The order doesn't change their quantity at all. If I were to write that in the geometry version, it's going to be the same thing, but the difference is I'm putting that segment bar on top and I'm using the congruent symbol. So even with congruency, it doesn't matter the order, it's still saying the same thing, that CD and AB have the same measure. for angles, if the measure of angle ABC is equal to the measure of angle DEG, then the measure of angle DEG is also equal to the measure of angle ABC. It's the same thing, I'm just doing it with angles. And the key here is when I switched into the geometry world, that M goes away, and I'm putting a congruent symbol instead. So the symmetric property allows us to change the order if we need to, because we need it to match what our proof statement is saying. Remember, reflexive properties, I can always state that an object is equal to itself. All right, transitive property. This one takes a little explanation, so I'm going to wait until we have some examples to kind of show you what it is. But for the algebra world, again, we're using this as our reason if we're going to apply the transitive property. And because it's the algebra world, it's going to have the equals. And for the geometry world, this will be our reason if we want to use this property, but it's going to have the congruent symbol. And I know it seems really silly, that small detail, but if we don't have that correct in our proof, then one of our reasons is wrong, not proving that my statement's right, therefore making the rest of my proof invalid. So make sure we pay attention to those small little details. So I'm going to do the number version here. And I want you guys to think of our law of syllogism. So transitive property is like the application of the law of syllogism in our proof. We will never ever use the law of syllogism as a reason. If we have something like that, we use transitive property. So, for instance, let me do an actual number example. So if I have 5 is equal to x, and x is equal to c, because these two are linked, I can just skip out the middleman, and I can write that 5 is equal to c. And that's the transitive property. Okay, remember, if the end of my statement is the same as the beginning of the next statement, it just becomes a middleman, it becomes a link that I can eliminate, and I can go from saying 5 straight to c. Okay, so if I were to write that in general, I could say if a equals b and b equals c, then I can conclude, since b is my link, I can conclude that a has to equal c. Again, there's no number version for geometry. We'll actually use this property a lot, so it's important that we practice this and make sure we understand the transitive property. So an example of segments, and this might make a little more sense. If I have segment AB is equal to segment CD, and I also know that segment CD is equal to segment EG, then I can conclude, since this is the link, if AB is equal to CD, so they're the same, and CD is equal to EG, they're the same. Well, if C has to be the same as AB, then that forces AB to also be the same as EG, since CD and EG are the same. I know that was a lot, but think of it as syllogism. This is the link, okay? This makes the CD is being the same as EG, and it's also the same as AB, so they all have to be the same for that to be true. So that's why I can conclude that AB is equal to EG. So for geometry, it's the same thing, but instead of the equal signs, I'm using congruent, and that means I need to put a bar on top of each of them. Okay, again, CD is the link, so that I can conclude that segment AB has to be congruent to segment AG. Angles work the same way, so I have the measure of angle ABC is equal to the measure of angle DEG, and the measure of angle DEG is equal to the measure of angle PST. Angle DEG links them together, so I can conclude that angle ABC is equal to the measure of angle PST. Okay. Angle DEG is forcing AB to be the same as PST because DEG also has to be equal to PST. If it has to be equal to both, that means all three are going to be the same. And then it's the same thing in algebra world, but I drop the M and I put the congruent symbol. DEG is the link, so that I can conclude that angle ABC is going to be congruent to angle PST. The common error that students make with transitive property is one, they write law of syllogism for the reason. Make sure you're writing transitive property for your reason if you're going to use it. And make sure you're using the equal or the congruent depending which world you're in. And the other common error is that they mistake it for substitution. Substitution and transitive looks very similar in a proof, but if you use the wrong reason, then again, your whole proof's going to be valid. So we need to make sure we understand the difference of what transitive looks like in a proof and what substitution looks like in a proof. So for transitive property, the equal expressions, so the one that's linking them, are going to be on opposite sides. Okay, so for example, if I'm given that AB plus BC equals AC, and I'm also given that DE is equal to AB plus BC, I'm going to need to write a conclusion for this. Okay. I know that AC and DE are going to be equal because both of them are equal to the same thing. They're both equal to AB plus BC. Okay, these are the equal expressions because they're the same expression. But if you look, they're on opposite sides. One is on the left, the left side of the equal sign, and the other one is on the right. Since they're on opposite sides of the equal sign, that's going to make it transitive property. So my conclusion would be that DE equals AC, and my reason, so by transitive property, and I'm in the algebra world, and I know that because there's an equal sign right here. So transitive property of equality. Substitution is similar, but the equal expressions are on the same side of the equal sign. So if I'm given the same thing, AB plus BC equals AC, and that AB plus BC equals DE. So it's the same thing, but the second one's flipped. I used my symmetric property there and I flipped it. So if I'm given that they are on the same side, so these two equal expressions are on the same side of the equal sign. Okay, so same side, both on the left. Okay, then when I'm going to conclude the same thing. AC is equal to DE, but my reason is going to be different. Since it's on the same side of the equal sign, my reason is substitution because I'm replacing. Okay, think of it as, you know, AB and BC equal AC. So when I see AB plus BC here, I'm replacing it with AC. Oh, and this would be substitution property of equality, because I'm still working with an equal sign. So there's examples there, example 1 and 2. Pause the video and try that for a minute or two. All right, so now that you've done that, I'm going to go through it real quick. My equal expression is measure of angle CBD, for example 1. They're on opposite sides of the equal sign. So I'm going to conclude that this is equal to this. So the measure of angle ABC is equal to the measure of angle DBE, because this is my length. Okay, but because it's on opposite sides, this is the transitive property of equality, because I'm working with a equal sign here. And when you did example 2, you should have seen that my equal expressions are on the same side. So again, those go away. And I'm left with segment DE plus segment FG is congruent to segment KL plus segment MN. But because it's on the same side, my property is substitution property. And this time I have congruent symbols, so it's substitution property of congruency. So hopefully you had the right thing. If you're struggling with it, you can come to Flex on Tuesday and ask questions. Or you can ask me in class. Linear pair postulate, we talked about this a little bit. We talked about the definition of linear pair and how it's really just a postulate for us to use it. So if two angles form a linear pair, then they are supplementary. Okay, so it's one of those fancy ones where we have to use a postulate and not the definition of. Okay, you will never ever write the definition of linear pair. You will always write linear pair postulate. So in example 3, I'm given a linear pair 1 and 2, and I know that because they're right next to each other and they create a line. So my conclusion, when I see linear pair, is going to be angle 1 and angle 2 are supplementary. And the reason being is that the second part is our conclusion, right? If I have the first part, if I know that this is a linear pair, then I can conclude the then part, our conclusion, right, is supplementary. It doesn't say equal to 180, so I can't add them up and equal it to 180. It says supplementary. So all I have to do is state that they're supplementary and give the reason as linear pair postulate. Now, if I needed to in a proof, I can write, after I give this statement, I can now say that the measure of angle 1 plus the measure of angle 2 equal 180. And my reason would be definition of supplementary because I have this here. But that's 2 steps ahead. So make sure if you see a linear pair, you're just stating that they're supplementary because that's all I can conclude over here. All right, vertical angles theorem, congruence theorem. If 2 angles are vertical angles, so if I know they're vertical angles, then they are congruent. Remember we talked about this a little bit, that I added in the sentence that they're congruent in the definition. It's not technically there. We actually had to prove that vertical angles were congruent first, and we will be doing that in the next unit. We're not ready for it quite yet. So we're just going to assume these things are true. That happens in life all the time. Think of like a little kid, if they hear thunder, they get scared, and the parents kind of make a funny metaphor. Like my mom always told me it was the angels bowling up in heaven. And it helped calm me because I was a young kid and freaked out. But now that I'm older and I understand science, I know that's not really true. But we assumed it was true when we were kids to help calm us down until we were smart enough and ready enough to understand the science behind it. So that's kind of what we're doing here with the linear pair postulate and the vertical angles congruent theorem, is we're going to assume they're true in this unit until we're stronger and better at proofs, so we could do those hard proofs in the next unit. All right, so if I'm going to use vertical angle theorem on this diagram, the only 2 I can say are vertical angles are 1 and 3. So I can clearly see that on my diagram. So if I see it on my diagram, I can just go straight to saying that angle 1 is congruent to angle 3. So in our proofs, we don't have to state that those angles are vertical. Same thing with linear pair postulate. I don't have to state that this is a linear pair because I can clearly see it in the diagram, and your reader will be able to see it in the diagram. Okay, same thing here with the vertical angles. I don't need to state that they're vertical angles. I can just see it in the diagram, and that diagram will be given to my reader. So I can go straight to just saying angle 1 and angle 3 are going to be congruent, and my reason is going to be vertical angles congruent theorem. Not definition of vertical angles. Okay, guys, linear pair and vertical angles are going to be special. They're going to be a theorem and a postulate. Okay? So make sure we write that down correctly. All right, our last page are some supplementary theorems that apparently I don't have on here. So I will be writing it. All right, so if 2 angles are supplementary, so that's the word you're filling in. Fill that word in. To the same angle, then they are congruent. And you're filling in congruent. So while you're filling that in, I'm going to write up example 1. So what this is saying is, if I know that angle 1 and angle 2 are supplementary, and angle 3 and angle 2 are supplementary, then, so right here where it says then, they are congruent. So I have 2 angles are supplementary to the same angle, then I can say that those two angles are congruent. So my same angle is angle 2 here. Okay. 1 is supplementary to 2. Right? 1 is supplementary to 2. And 2 is still the same, and it's supplementary to 3. Okay, so they each make a line together. What happens is, well, 1 and 3 become vertical angles, and because of vertical angle theorem, I know they're congruent. But that's a lot of steps to go through to prove that 1 and 3 are congruent. So in a proof, we can use this theorem here and go straight there and kind of skip some steps. So it's a shortcut. So I can use that theorem, and I can take a shortcut and say that angle 1 is congruent to angle 3 without having to state first or prove first that they're vertical angles. As long as my reason is if two angles are supplementary to same angle, then they are congruent. Okay, so all I did was I rewrote this theorem. I just kind of abbreviated some things. If I write that theorem, it's a shortcut, and I don't have to prove that these two angles are vertical first. Okay, I can just go straight to saying that angle 1 is congruent to angle 3. All right, I'm going to use some of this still for the second theorem. So the second theorem says if two angles, the second theorem says if two angles are supplementary to congruent angles, then they are congruent. Okay, so an example of that would be if I know that angle 2 is congruent to angle 4, and angle 1 is angle 1 and angle 2 are supplementary. And angle 3 and angle 4 are supplementary. You have this written on your paper already. This is the example number 5. Okay, so if I know 2 and 4 are congruent, and angle 1 and angle 2 are supplementary, and angle 3 and angle 4 are supplementary, these two angles I can replace either way. So I can make this angle 2 if I want, because I can use substitution or transitive property. And now it's just like the first example where these now are the same, so they have to be congruent. So it's just another way, another shortcut to say that angle 1 is congruent to angle 3. So even if these two angles here are different, as long as I know that they are congruent, I'm given this, okay, I can still say that angle 1 and angle 3 are congruent, and I just use this. If two angles are supplementary to congruent angles, then they are congruent. Which is, again, just this theorem up here, just abbreviated. Okay, so make sure you fill in the word supplementary and the word congruent again. All right. So again, this allows us to skip a bunch of steps that we would normally need to show in our proofs. It's a shortcut. The last sentence on your note says both theorems can be used for, and it has a blank. That blank, you need to fill it in with the word complementary. Okay, so both these theorems you can use even if the angles are complementary. So you just replace this part here with complementary when you want to use it. So you guys need to put some of this in your proof list. So let's grab that. So on the front page, on the second box, we have algebraic and geometric properties. We have some filled in already. We have to fill in 3 more. We have the, oh, is that gonna let me work? All right, hold on a second. I'm gonna move that over to the smartboard. All right, so we're going to fill in those last 3 bullet points for the properties of equality. You're going to put symmetric, property of equality. You are going to put transitive, property of equality, and you're going to put reflexive, property of equality. In the geometry world, we're going to write those down too. So symmetric, property of congruency, transitive, property of congruency, reflexive, property of congruency, and then we're also going to put substitution, property of congruency. Okay. So make sure you add those onto your sheet. If you need to pause the video, you can. Flip to the back. We're going to fill in geometric postulates and theorems. We need to fill in our linear pair postulate. And we need to fill in vertical angles congruent theorem. Right there at the top on the back. Okay. They're on the back with postulates and theorems, so hopefully remind you guys that it's not definitions, and that's why it's not going in the definition box. Okay. That is it for today's notes. If you feel like you need help with some of this stuff, please reach out to me on Tuesday during class, or come into Flex on Tuesday so I can help you. It was a lot of just sitting and getting, and hopefully on Tuesday when we start writing proofs and actually applying these theorems and properties, it'll make a little more sense. Okay, I hope you guys have a wonderful weekend. I look forward to seeing you guys on Tuesday.